I noticed yesterday when I was listening back to some of my old lectures that every stats class I started out like this. Okay, so I'm not going to do that. We're going to talk about, like I said, there's two short ones today, one on postdocs and one on transformations. So, okay, let's say you've got a significant F. Did I just say okay? Yeah, see, I do it, it's instinctive, it happens to me. I'm sorry, I apologize to the listeners and all the people throughout the world. And babies, also the babies and puppies. I don't know. I've said before, I'm just trying to entertain myself at this point. You have a significant F. Now what do you do? So you found out, remember the F has the null hypothesis of an analysis variance is that mu1 equals mu2 equals mu3 equals ... equals mu k. Just that all the means are equal. And then when you get a significant F, all that says is that isn't true. It just says at least two of the means are different. Right? So there's our HO. But our HA doesn't say which two are different. We don't know that. Which two means are different from each other? Or maybe they're all different from each other. Or maybe two are different and one is the same. Three of these things are not like the others. It's like Sesame Street. They probably changed Sesame Street by now, right? So you don't even know that. You don't even know what Sesame Street is. My cultural references are dead. I may as well be talking about the 1940s. When all this was developed. See, I tied it back to the class. That's what a good teacher does. So, but that's a question you might want to know, right? Like the null hypothesis is that all the means are different. The same. The HA is that at least two are different, but doesn't say which two. And you might want to know that. You might not want to, right? You might look at something. Oftentimes, you'll have, like, say, two control groups and an experimental group, and you'll go, well, it's pretty clear the experimental group's way up here. These two are way down here. Not really interesting to go any further. I know the two control groups should be the same, and the difference is here. I can see it. I'm not an idiot. I can read a graph. Game over. But you might want to do something else. So one of the procedures, probably the simplest procedure, is called the Bonferroni. You ever had the Bonferroni? It's just delicious. But I make that joke. Totally for me, as most of them are. So you could do a whole bunch of t-tests, couldn't you? But that would kind of defeat the purpose of the analysis of variance. So if you did a bunch of t-tests, the alpha level goes up, right? Because you're making all these comparisons. Yes? Make sense? So if I have three groups, now I've got to compare group 1 to group 2, group 2 to group 3, and group 1 to group 3. I'm going to do 3 t-tests. If I do, let's say, 20 t-tests, let's say, and that could happen with about 5 times 4, 2, roughly with 4 groups, you're starting to get close to doing like 15, 20 t-tests, if you're comparing them. Wow. If I do more than 20 and I have an alpha level of 0.05, almost definitionally at this point, I have one that is just by random chance, just because of the way statistics works. I find a significant difference and actually isn't one. So what I want to do, what the Bonferroni procedure does, is it takes this into account. The Bonferroni T procedure basically just changes the alpha level. It's 1 over n times alpha. And n is the number of what are called corrections, the number of comparisons you're doing. Now, you might not do all the possible comparisons. Like, if you were interested, like I said, you've got, say, 3, let's say you have 4 groups, but 3 of them are control groups. And you might think, when the hell does that happen? A lot of times in drug studies that happens. So you've got one group that's given the drug, and let's say they're rats, to make this easy. So one group is rats that are given the drug, one group is rats not given the drug, one group is rats given a sham injection, so they're picked up, they're shown the needle, and they're not injected, and the final group is they're picked up, shown the needle, and injected the same needle. Those are 3 control groups. All I care about is it different than one of the control groups. So I might be just doing 1, maybe I'm doing 2. Is it different than the regular control and the saline control? So instead of maybe doing 5 tests or something, I'm just doing 2. So that would be n in this case is 2. And then it just corrects the alpha level, and then you're just doing a t-test. Okay? So it's just a t-test. It's called t prime. That's what the little thing is there. And it's just x bar 1 minus x bar 2 divided by the square root of 2 times mean squared error over n. And why is it 2? Well, remember when you add two variances together? If we were doing a two-group t-test, we'd have s squared sub 1 over n1 plus s squared sub 2 over n2. That's all we've done here. We've got the estimate of the variance twice. And then you look up in what's called a Bonferroni table, or frankly, your software does it for you. You just choose Bonferroni as one of what it calls post hocs. And it tells you if it's significant, which comparisons you. Okay? That's the most basic one. I'm never going to ask, no one does this by hand, don't worry about it. Don't worry about memorizing any formulas or anything like that. I may ask you what a quiz, what a post hoc test is. Pretty good guess, actually, that I ask you that. But I'm not going to say what's the formula for the Bonferroni T procedure, because I don't know it unless I look at it.
Dave.
Yes?
What do you mean by number of corrections?
So it's the number of comparisons you do.
Okay.
Yep. Because you're correcting the alpha level, that's why it's called a correction. So if it's like, if you're doing 3, it's going to be 1 over 3 times 0.05. So now it becomes 0.15, 0.015, sorry. Right? That's wrong.
So will that change this t-test, or does the t-test always remain the same?
The t-test is going to look like this. That's how you're going to calculate it. It's going to change the alpha level of the t-test you're doing. You can see there's an issue here that if you're doing enough comparisons, these t's become so small, the alpha levels become so small that you can't find a difference even if it's there. Mm-hmm. Right? So this is used when you're going to compare, you got maybe 5, 6 groups, and you want to compare 3 of them or 2 of them only after you've found a significant. You could do this. That should look vaguely familiar. It looks exactly the same as the other one, except instead of 2 times mean square error, I just got mean square error. And I'm comparing the largest mean to the smallest mean. And I get a value called the studentized range. And I get a value called Q. And it knows everything and it runs the universe. Star Trek? Nobody? And moving on. You then look up to see in a table what this value, this gives you a value, this studentized range, and then you say, okay, how big is the number? It gives you like a range of how big the largest to the smallest one, are they different? So it just gives you like a, let's say it's a 7, and then that means all means greater than mean different by more than 7. It looks like you look at the table, are significantly different from each other. Again, it's still automatic. Pretty straightforward. It's just, again, this is how it's calculated. No one's going to ever ask you to do this. Or you can do what's called the student Newman Keuls test. This is in the few times that I've played with analysis of variance with anger. So actually for research, this is what I've used. And it looks like this. You look up a Q value, again, in a table. R is the number of comparisons you're doing, 0.05 degrees of freedom, and you get this W value. And that just tells you how big of W sub R, that's the range. Okay? So any set of comparisons with range of R, it gives you a number. So the value you get out is like 11. And that means all means that differ by at least 11 are different, significantly different from each other. So any set of comparisons with range R. Or let's say 3 instead of 11. There's another one like this, which is called one that Tukey developed, which is exceedingly similar to this. It just uses the largest range. This is going to be, it looks a lot like, well, it looks just like this, but it always uses the largest possible range, largest to smallest. And HSD stands for honestly significantly different. It actually does, because Tukey was clever. Because there's another test called the LSD test. It's not about acid, it's least significant difference. And then Tukey came along and said, I'm going to be clever, and I'll call mine honestly significantly different. Basically, all these things are doing, they're all variations on t-tests, basically, because you can always see that there's a term in every formula that has the square root of mean squared error divided by n. So square root of variance divided by n, which is what a t-test always has. They're just variations on t-tests. That's all they are. Now, I will say that that some people, and those people kind of include me, believe that this is all a waste of time. That's a philosophical thing. If you were interested in a comparison between this group and this group over here, just do that damn experiment. That's my view. Because what ANOVA is going to give you is, what's the pattern in your data look like? Is it different than everything's the same? So if that's the question you're asking, that's all you should care about. Right? But that's what's called a minority opinion. Most people want you to do post hoc tests. It's a minority opinion I learned from my stats prof in grad school. That's one of and I have great respect for him, and he knows more about stats than I do, so I figure he's probably right. I wouldn't worry a great deal about these things. They're easy to do. You might ask yourself, though, which comparison should I use? Well, most people do. You do all of them and find out which one fits their data. That's not what you're supposed to do. Right? That's getting perilously close to something called p-hacking, which is when it's like, oh, p's at 0.06? Well, let's run more subjects until it gets to 0.05. Don't do that. That's kind of what you're doing here. I'd stick to one in a paper. So if you're writing a paper, doing your thesis, don't say, then I went over to this one, and then in this experiment, I'm using different post hoc tests. The first thing I'm going to look at that when I read that is, why? And then the answer you would give probably is, well, it showed what I thought it would here, the other one fits with my hypothesis here, and then that means you're being a dishonest jerk. So stick with the same one. I've used HSD. A lot of people use that, but the other ones are fine. There's nothing wrong with it. HSD is probably the least, it's in the middle as far as how conservative it is. Bonferroni is a very conservative test. When you get the number of groups get large because the corrections, the alpha level gets really small. Right? So it's hard to find differences. Newman Keuls is a little bit more liberal. HSD is a little more liberal than that. Then there are ones that are even way more that they find. Sometimes, by the way, this is why I don't like these things. Sometimes you will have a significant F, and none of the post hoc tests show you that groups are different. And it's like, well, how can that be? Other times, if you take data where you've done analysis of variance and you find an effect, so you find no effect, but then for the hell of it you do post hocs, sometimes they find significant effects that literally aren't there. This is why I don't trust these things. I'm not big on these things. Nonetheless, let's make them wrong, and you will usually be asked, even know what, like, let's say that you do your thesis with me and you do an analysis of variance, and I'm going to say I don't care about post hoc tests. If the pattern looks good, it's exactly what we expected. And then you're going to go do your practice talk in front of the other faculty members when you nail down how you do on for your public lecture, on your public presentation, on your talk. And if you haven't done one, someone's going to say, well, do you need post hocs? And then you get watch me get into an argument with Cheryl about post hoc tests, which is no fun for you to say. So you just do it. All right? Questions about that stuff? So there's one short lecture for today.